Hello, this is Nicholas, and I wanted to show a way to remember the product of sum identities for integrals. In other words, I wanted to derive, there shouldn't be a hyphen there, to derive those identities. So if you remember them, and I actually don't know off the top of my head what these identities even look like, but what we can do is, if you remember what they look like at all, they have a sine of a plus b, or a sine of a minus b, a cosine of a plus b, or a cosine of a minus b. So, now we have identities for these four right here. So what are they? Sine of a plus b, and you really should have these memorized. So hopefully there is a way to derive these that I know of off the top of my head as well, and I might show that at the end. But this is sine a cosine b plus cosine a sine b, and this is sine a minus b, which is the same exact thing, but instead of a plus we have a minus sign. So to me, it would make sense if I add these two, this is going to cancel. And so now I get the product of sum identity for sine a cosine b. So this tells us that sine a plus b plus sine a minus b is 2 sine a cosine b, and of course we can just divide by a 2. And this is the product of sum identity for sine a cosine b. Cool. If I subtracted the two, let's try that now. If instead I subtracted these two, then this would cancel, and I would have a minus a negative right here, so that would become a positive. So if I were to subtract those two, I get that sine of a plus b minus sine of a minus b is 2 cosine a sine b, because I had minus a negative, and just like that we can divide by a 2 here, and we get the next product to sum identity for cosine a sine b. The other two cases, I'm sure you could probably just guess by now, come from the cosine angle addition and subtraction formulas. So if you recall those, cosine a plus b is cosine a cosine b minus sine a sine b. And this is the same exact thing, but it's got a plus sign instead. So we're just going to add and subtract this. So first, I think it would make sense to add them. So we get cosine of a plus b plus cosine of a minus b is, this cancels out, and we get 2 cosine a cosine b. So cosine a cosine b is this here over 2. And lastly, we can subtract these two, so that will cancel, and we get cosine a plus b minus cosine of a minus b is, now here we have minus, and then a minus. So we're going to have a minus 2 here. Oops, I'm still on the laser. Minus 2. This is the only one with a negative, which is just odd, but it's there. Negative 2 sine A, sine B, and we can divide by a negative 2. Oops. Negative 2. And I would just simplify this one more step. I would say that sine A, sine B is instead equal to cosine of A minus B minus minus cosine of A plus B over 2. So in other words, I just took the negative sign, put it in the numerator, and then multiplied the negative 1 by the numerator, so the sign changed on each of the terms. And that right there is the 4 sum to product identities. It's really as easy as that. Now, if these first 4 identities here are not engraved into your mind, or if you're looking for maybe a new way to derive them, I am going to show that. So, and my derivation relies on DeMoivre's, it looks like DeMoivre's theorem, but it's DeMoivre's theorem. And DeMoivre's theorem, the powerhouse behind DeMoivre's theorem at least, is the fact that e to the I theta is, maybe you've seen it called cis theta, is cosine theta plus I times the sine of theta. And so what it says that if I have, see, normally you use it in polar coordinates. So like, for example, if I had 1 plus I to the 2020, I could, I would draw a diagram here, and then this is length 1, this is length I with magnitude 1. And so that angle there, theta, would be pi over 4. And this length would be root 2, Pythagorean theorem. And so I could write 1 plus I to the 2020 as square root 2 cis pi over 4 to the 2020. And so what DeMoivre's theorem says is that if I have cis theta to the n, that is the same thing, and remember cis theta is cosine theta plus I sine theta. That's the same thing as cis n theta. Why is that? It's because of the fact that that is equivalent to e to the I theta. Because e to the I theta, it's just a property of exponents. E to the I theta to the n is e to the I times n theta. So now the angle, instead of theta, it's n theta. So we get cosine of n theta plus I times the sine of n theta. So it's a property of exponents, is why DeMoivre's theorem is actually true. Now, in order to prove that these two are true, I need calculus that, at least for a Calc 2 class, won't learn until the end of the year. So I'm not going to prove that. The video was originally on just proving the sum to product identities. But if you give me DeMoivre's theorem, then I can prove the trig identities in maybe an unconventional way. I'm not sure how aware you guys are of this. But returning to this here, this root 2 cis pi over 4 to the 2020 then is just, well, it's 2 to the 1010 because root 2 to the 2020 is the same thing as 2 to the 1010. And we have cis of 2020 times pi over 4. And 2020 divided by 4 is 505. So that's actually 2 to the 1010. And cis of 505 pi is coterminal to cis pi. And cis pi is 2 to the 10,010 times cis pi. Cosine of pi is (-1) plus I sine pi. Sine pi is 0, so that's 0 times I, which is 0. So this thing here simplifies to just (-2 to the 10,010, which is a pretty cool simplification, I would say. So, sum to product identities, we can use the fact, what can we use? We know that e to the I times a plus b is cis a plus b. Well, this is cosine of a plus b plus I times the sine of a plus b. What do I want to do from here? Maybe I could make this e to the IA, because we're doing IAs, times e to the IB, because we're in IB. Okay, sorry, which is cosine A, cosine A plus I sine A. I think this is how I did it. And then these are being multiplied, so times cosine of b plus I sine b. I am pretty sure this is how I did it. This is ringing a bell to me. So cosine of a plus b plus I times the sine of a plus b is, now if I FOIL this here, if I FOIL that there, I get a cosine A, cosine B. Outer now becomes plus I cosine A sine B. The inner is plus I sine A cosine of B. And the last is negative sine A sine B. Now this may look like a mess, but it's actually very nice, and I actually have the identity derived now, if you can't already tell. It comes from the fact that, and it's a relatively obvious fact, but it's a very powerful fact, it's the equivalence of complex numbers. In other words, a plus bi is equal to c plus di if and only if a is equal to b and c is, or I'm sorry, if a is equal to c and b is equal to d. Because if c is a, then I would get a plus bi is equal to c, which is just a, plus d, which is just bi, and reflexive property makes it true. So this is a pretty trivial fact, right? You would have guessed this, but it helps us narrow down this problem much, much, much easy. It reframes it in a much better way. So this, we can look at this nasty expression here, and we can just equate the real parts to this and the imaginary parts to that. So in other words, and I'll do it in right here, cosine of a plus b, I'm looking at the real parts, which is this. So this tells me that cosine of a plus b is cosine A, cosine b, minus sine A, sine b. Just by looking at the real parts of this equation here and using the definition of the equivalence of complex numbers. And so likewise, now I'm looking at the imaginary parts, so anything that has an I. This and that. So this tells me that sine of a plus b is, and normally we see it written this way. I'm flipping the order. This term here is first instead of this term, but normally it's written the other way, so I'll write it that way. That's sine A cosine B plus cosine A sine B. And that is a way to remember the cosine angle addition formulas. It's pretty cool. And you can actually do you can do this for the double angle formulas as well, right? Just using the fact that e to the I theta squared is e to the 2 theta I, you could say that cosine theta plus I sine theta squared is cosine 2 theta plus I sine 2 theta. And you could do, almost verbatim what I did up here, except all you're going to do is you're just going to be looking at cosine 2 theta and sine 2 theta instead, but the process it's exactly the same. It's exactly the same. So this is a way to remember those pesky integration formulas that might show up on our tests. So I hope you enjoyed.